Hello there, welcome to the Learning of Engineering tutorial video lecture. In continuation of the previous video lecture of a cantilever beam is subjected to the uniform distributed load. The uniform distributed load, it is spreaded on the area or the surface or the plane of the particular object. We can say that is going to be the distributed load. So here the cantilever beam is subjected to the uniform distributed load over the length of 1.5 meters. We know A is the fixed end and the B is the free end. From the free end B, it is spreaded over a length of 1.5 meters and it is carrying the 1 kilonewton per meters. And the total length of the beam is going to be 2 meters. Now we need to find out the shear forces and the bending moments which are acting on this member. That's we need to calculate. So as you know, the procedure of that, the first initially we need to take the one member, that means we need to take the one section so that we are trying to take it. So that what I am going to do, I am taking the one section that is going to be the point C. Suppose the point C, it is located at a distance of x distance, it is there, suppose. So can you see here, that is going to be x distance, it is there. So for this one I want to find out the shear force. We know it is going to be existed 1 kilonewton meter, but when it comes to the shear force, it is available in newtons itself. What I am going to do, I want to multiply the length of that member so that we are going to be getting that. What is that? Fx, this is going to be the shear force at the considered section x, that is equal to, and here that we got it, the distributed load into x we are getting. What is the amount of the distributed load here? That is equal to, so that is equal to 1 kilonewton per meter. And what is the x here? That's we are going to be substituting the different boundary conditions. What are that? X is equal to 0 and x is equal to 1.5 meters. That's we are going to be adding. So for this one, if I am going to be substituting, so that f of x is equal to, and here the 1 kilonewtons, that is equal to x, we got it. In the first case, x is equal to 0, I am substituting. If I am going to be substituting x is equal to 0, so then what will happen at the point B? So FB is equal to 1 into 0, then I got the 0 shear force at B. And now I am going to be substituting the second one, x is equal to 1.5 meters. If I am substituting 1.5 meters, that's FC is equal to, this is FC, we consider there, then we can consider this is when the point is the D point. Suppose that FD is equal to 1 into 1.5 meters. So then 1.5 kilonewtons we got it. And similarly at the third point, if I am going to be considering here FA. So in this case there is no shear force existed between the A and D. That is, there is no load acting between the points A and D. So then what happened? FA also we are getting 1.5 kilonewtons. This is the FA, this is the FD forces, we got it. Right? So that we can draw the shear force diagram. And similarly, we have to do the bending moments. How could you find out the bending moments? Again, we are going to be considering the bending moments at this section. So how could you write it? The bending moment at section mx is equal to, that is going to be bending moment at x is equal to fx into perpendicular distance, we have to take it. So how could you take it, that perpendicular distance? That's going to be fx into x by 2 we are getting. Right? What is the fx here? That's fx is equal to w into x square by 2, we got it. Right? This is going to be your mx. Now what I am going to do? I am going to be substituting the values. At x is equal to 0, then that is going to be your mb is equal to w, so that is going to be distributed load is going to be 1 kilonewton meter into 0 by 2, we got the 0. So that is going to be the bending moments at B is equal to 0. Now I want to find out at D. So that is going to be your dx is equal to 1.5 meters. Then md is equal to 1 into 1.5 whole square by 2. Then finally I am going to be getting that equation is around 1.125 Newton meters. We got it. Meters we are getting. And similarly, that I want to find out the moments at A is equal to, what is the formula we do have? That's going to be, this formula I am going to be taking here. W is nothing but, that's going to be 1 kilonewton meter. So, into, it is spreaded over a length of 1.5 meters, right? So, this is going to be the load, and this is the length of the load is distributed. Then what the distance the center is going to be existed. So that I am going to be taking here, that's going to be here 1.5 divided by 2 plus 0.5 I am going to be taking. So from this one 1.5 and here 1.125 we are getting. So finally MA is equal to 1.1875 the Newton meters, we got it. So there we can see the moments calculating for the A is going to be is in this way, right? This is going to be converted into the point load, and then that the center of the distributed load we have taken from the point X to the A distance is going to be, the total length is going to be 1.5 meters by 2, that means going to be center I am getting, and it is also located at a distance of 0.5 meters. So then totally this is going to be the 0.75 and here is the 0.5. So then we got it this one. Now I am going to be draw the shear force diagram as well as the bending moment diagram. So now I am trying to draw the shear force diagram. As we know, the shear force at point B is equal to 0, we got it, and similarly at 1.5 meters. So that's going to be at the point D, the shear force is equal to the 1.5 kilonewtons. So that I am going to be taking here 1.5 kilonewtons. And similarly at FA also we got the 1.5 kilonewtons. So that I am going to be taking here, this is also 1.5 kilonewtons. So in between there is no load, so then the constant line we are going to be horizontal line we are going to be getting. And similarly between these two the distributed load is there, that's going to be inclined line we can see, right? That is going to be your shear force at point A and the D and the B. Now I am going to be taking, this is the SFD we are going to be calling. Similarly I am trying to go with the bending moment diagram. As we know, the bending moment at B is equal to 0, right? All these values we are getting the negative because these are going to be trying to move in the clockwise direction. As we discussed, the clockwise directions always the negative sign. So at D is equal to 1.125. So this is going to be 1.125 kilonewton meter. And similarly MA is equal to 1.187, suppose I am going to be getting here, it's going to be 1.1875. So this is the point A, D and D. So then can you see here between D and B the line is going to be inclined one. So that's why we are going to be taking, so now we are going to be taking here is going to be parabolic curve. The parabolic curve is going to be coming, but here the line is going to be constant. So then here the order of the line is going to be coming here is going to be inclined one, right? So this is going to be your bending moment diagram. So there we can see, you can calculate at any point of the beam the shear force as well as the bending moment by taking the projections to here. Suppose if you draw the projections here, those touching points are going to be the magnitudes we are getting. So this is the way we are going to be calculating the shear force as well as the bending moment. So stay tuned for the more updates regarding the shear force as well as the bending moment diagrams. Thank you.